All right, so now is noon. So welcome everybody. We are so excited to have Brendan Rose to be our host this time and to talk about the Superspace coinvariance and delta operator modules. I think some conjectures on that too, right?
Yes.
All right, so all yours.
Well, thank you very much. And thank you for the invitation to speak in this seminar. There have been some really beautiful talks so far. In a sense, it's a pretty hard act to follow. So I'm actually only going to be giving 2 talks. And I mean, partially this is because a lot of what I'll be talking about remains not only conjectural, but I would say frustratingly conjectural. There are a lot of things that we really feel that we should prove only with the right perspective, but it's somehow remained elusive. Perhaps the main reference for what I'll be talking about today and next time is this paper, Vandermon's in Superspace, which I wrote with Andy Wilson. Although what I'll be talking about for most of today will really be sort of a prehistory leading up to this paper. So, you know, I guess as Anna said at the beginning of her talk, I'm aware that there are a lot of experts that are in the audience. So I hope you guys will indulge me when I talk about material that you've somehow known for a while, but I do want to make this accessible. So if you guys have any questions, please interrupt and let me know. All right. So what I'm going to be talking about is, well, in many ways tied to coinvariant theory. So I'd like to remind you guys about the classical coinvariant ring. So the classical coinvariant ring. And this is an object that appeared as a very special case of these quotient rings or these cohomology rings introduced in John's talk. So we're going to think about a polynomial ring in variables. I'll work over the complex numbers. Your choice of field won't really matter too much. And I'll abbreviate these n variables, these x's with a capital Xn. And this is a ring which carries a natural action of the symmetric group Sn, right? So we have this action of Sn on our ring, and we're going to think about the quotient of our ring by a certain ideal. And well, morally, what we want to do is we want to think about the subspace of Sn invariants. Somehow invariants are relatively boring when it comes to a group action. Well, they're not really boring, but you know, in some sense, nothing gets changed. We want to kind of mod out by that thing. But because constant polynomials are invariant, we have to throw in a condition that we only look at those invariants with a vanishing constant term. So we're going to look at this quotient. And if you want to kind of interact with your computer, right, kind of put this quotient ring into a computer, try to learn things about it that way. I mean, this is, of course, a very nice conceptual formulation for what this quotient is, but we're actually going to want generators for this ideal. And one choice of generators that you can make is given by the n elementary symmetric polynomials like so. And this is a quotient ring we're going to call Rn. Okay, so this is the classical coinvariant ring. We have invariants, we're modding out by them. So what we have are coinvariants. And what kind of an object is this? So it's a quotient ring, and because I'm modding out by a homogeneous ideal, it is in fact a graded quotient ring. And because my ideal is invariant under the action of the symmetric group, what I get is in fact a graded Sn module. So this is going to be a graded Sn module. And we have some very classical results about this module. So Chevalier says that if I look at Rn as, whoa, what was that? If I look at Rn as an ungraded SN module, right? What I get is the regular representation of SN. And Chevalier actually used Galois theory to prove this, something called the normal basis theorem. Next up, we have a result of Artin. And this is the father, not the son, Emil Artin. And this result says, well, we have a graded ring. It's a graded vector space in particular. And we can talk about the Hilbert series, and it's the most natural thing in the world. It's the Q analog of n factorial. So this has come up in a couple of talks before. And then you might wonder what happens when we put these two structures together. Well, there's a result of Lustig, Stanley, that says that if I'm interested in the graded character of this module, so I'm looking at the graded Frobenius image of Rn, and I have to have my little grading tracker Q there. Well, I can express this combinatorially as a sum over standard Young-Tableau T within boxes of, well, a Schur function corresponding to the shape of T, right? So that's kind of tracking my irreducible, basically. And now I have a major index statistic on standard Young-Tableau. It's just the sum of the descents of a standard tableau. And I put a Q to the major index right there. So that's a combinatorial expression for this object, but we all saw a beautiful lecture series from Anna about the theory of cattle animals. And this is in fact a very special cat, right? This is going to be this kind of Hall-Littlewood cat corresponding to a single column in a variable set X with a tracker Q. So this is one version of the Hall-Littlewood polynomials. Okay, so that's some pretty classical material. I hope it is maybe somewhat familiar. And just sort of for completeness, to tie in a little bit with what John was talking about, there's a result of Borel, which states that if I look at the full flag variety of complete flags in C to the n, I'll denote that by FLN. And if I look at its cohomology ring, say with coefficients in C, although in this context I could have taken integer coefficients, that would have been fine, that can be presented as Rn. And there's an explicit presentation that identifies the variables with certain Chern classes living inside this cohomology. All right, so these are the classical coinvariants. Maybe this is a good place to pause for a sec. Should open the chat. I haven't taught for a while, so I'm not used to having the chat open and behaving like a YouTube influencer.
One small question. Can you hear me?
Yes? Sure. Yes, I can.
So you can define coinvariants for other group actions.
Certainly.
Are there some results in this list that generalize to other group actions? Chevalier, I don't know.
Oh, yes, yes. And thank you very much for asking that question. Absolutely. So let me make a little bit of a remark. And I mean, this will come up sort of later. we can take Sn and promote it to a subgroup G of GLNC. And I'm not going to just take any matrix group. I'm going to assume that G is a finite complex reflection group. So this is a finite subgroup of my group of n by n invertible complex matrices, which is generated by reflections, where now the word reflection must be interpreted in the complex sense. Reflection here means conjugate to a matrix of this form, where here zeta is some root of unity having finite order. So in the real case, zeta would always be -1. Okay, so you can take Sn and you can promote it to a reflection group like this. You have G, which still acts on the polynomial ring C brackets Xn, now by linear substitutions. C brackets Xn super G, if I look at these invariants, there's a crucial result of Chevalier that says that this invariant ring is itself a polynomial ring and a system of so-called fundamental invariants. So these are algebraically independent, homogeneous invariant polynomials, which generate the invariant ring. So in the case of Sn, you could think about these as being the elementary symmetric polynomials of the power sums. And not only that, but if I take C brackets Xn and I mod out by these invariants with vanishing constant term, what I have here is now not a graded Sn module, but a graded G module. And as an ungraded G module, what I get is the regular representation, and both of these are results of Claude-Chevalier. Does that help? Or
yes, thank you.
You're welcome. Any other questions? Thank you for asking that.
And does this extend to Lie groups?
Does this extend to Lie groups? Right. You know, I think that's a little bit trickier, right? So, I mean, if I think about something like GLN, you know, the GLN invariant polynomials are just going to be constants. So not in an interesting way, in a naive sense. So yeah, I guess off the top of my head, I can't think of a very direct way to generalize this theory to Lie groups, but it's a good question, Teddy.
Thank you. Right.
You're welcome. I mean, maybe one way to say this is if you look at this flag manifold, right, FLN, the flag manifold generalizes to any Lie group, right? So you can take G mod B, where G is your Lie group and B is your Borel. And Borel's theorem extends in that case. So if I were to present the cohomology ring of G mod B, what I would have is the co-invariant ring labeled by the corresponding file group. So maybe that's the best possible answer I can give.
Okay, thank you.
You're welcome. All right, so some kind of classical stuff that's maybe good to review it. Okay, so now we get into the world of Q and T. So we can talk about diagonal coinvariance. So the idea here is that I have a polynomial ring with nx variables and also ny variables. And Garcia and Heyman considered a diagonal action of Sn on this ring, right? So W is going to send Xi to XW of I, and simultaneously Yi to YW of I. And what's DRN? Well, it's what you get by playing essentially the same game. You say that, well, I have a polynomial ring and these two sets of invariables, and I'm going to mod out by the Sn invariance with vanishing constant term. And once more, we have kind of a nice generating set of this ideal, the so-called polarized power sum. So this was known to Weil. So the idea is I'm going to fix two numbers A and B, and I'm going to look at an invariant that looks as follows. So I'll just sum up Xi to the A, Yi to the B. So it's kind of like a power sum, but I have two sets of variables now. And I have these two parameters A and B, and this will always be invariant, but I'm only allowed to consider invariants with vanishing constant terms, so I had better assume that A plus B is actually positive. So I'd say, and this is coming from work of Weil. All right, so now what I have is a doubly graded Sn module with one grading coming from the x's and another grading coming from the y's. And we can try to ask the same questions about it. So for example, what is this thing as an ungraded Sn module? And this was Heyman's work. So as ungraded, oops, Sn modules, DRN is isomorphic to, well, we're not going to have the regular representation of Sn anymore. We're going to have something bigger. Namely, we're going to have this set of size n parking functions or length n parking functions. So you can think about these as length n sequences of positive integers whose non-decreasing rearrangement fits below the staircase 1, 2, 3, 4 up through n. So this carries a permutation action of Sn, and this is almost correct, but you have to twist by the sign representation. So this is a result of Heyman. And Heyman also tells you, well, what if I'm interested in the doubly graded Frobenius image? So in this setting, I need two variables to track my grading, one to track the X grading, one to track the Y grading. So Q here is keeping track of my X grading, whereas T is keeping track of my Y grading. And Heyman says that this is the same thing as nabla En. So nabla is this Macdonald eigenoperator that appeared in Anna's talks, right? So if I want to compute this thing, I have to take En, write it in terms of modified Macdonald polynomials. Then I apply this operator nabla. It has a certain predictable eigenvalue on any modified Macdonald. And now I would have this big expression in terms of modified Macdonalds. And of course, what you would really want for a Frobenius image would be something like the Schur expansion. That would be something like, well, what is the actual decomposition into irreducibles? And this is a major open problem. I mean, open to the point where we don't even really have a conjecture. The state of the art is essentially Hagelin's QT Schroeder theorem. So Jim's theorem tells you what are the bigraded multiplicities of the hook-shaped irreducibles. I think there are things you can also say for 2 rows, but we're really pretty far away from even a guess for what the Schur expansion ought to be. Okay, so if we're a little bit less ambitious, if we don't want the whole bigraded SN structure, and maybe we just want the bigraded vector space structure, well, there's a result which I'll attribute to Carlson-Mellett. It's a consequence of their proof of the shuffle theorem, and it was proven in a different way by Carlson and Blomkov. And it says that the bigraded Hilbert series of DRN and Q and T is going to be a sum over parking functions of Q to the area of P, T to another statistic, the dm of P. So we've seen these area and diagonal inversion statistics, again, appearing in Anna's talks in much greater generality. But the shuffle theorem is basically telling you, in particular, how can I take the inner product of nabla En with P1 to the N, and this is what you would actually get. So I'll say that this proof, so it relies on the work of Heyman and also uses the shuffle theorem. So this shuffle theorem is like what they proved, and this is a corollary of it. Now the Carlson and Blomkov thing, this is, if I had to have a top 10 list of papers that I think should receive more attention in our community, Carlson and Blomkov, that this really would be on it. And it's on it because their proof was actually independent of the work of Heyman, right? So this uses the geometry of affine Springer fibers. So these are certain geometric objects. They have a nice affine paving due to Listig and Smelt. And they actually found an independent proof of this result. And to this day, this is the only proof that, for example, the vector space dimension of DRN is n+1 to the n-1 that doesn't use isospectral Hilbert schemes. So you're still using geometry, but I hope it's not too controversial to say, this geometry feels like it's a little bit more tractable than what Mark Heyman did, right? So I think that people really should be looking at this point of view. And kind of another interesting aspect is that the isospectral Hilbert scheme perspective leads to nabla En, right? It leads to this operator theoretic object, in the world of symmetric function operators. The affine Springer fibers perspective leads naturally to this thing, to this combinatorial expression involving area and dm von parking functions. So I think this paper really does deserve more attention. And in terms of the result of Borel geometry, you could either say Hilbert schemes or Springer fibers, and I won't say much else beyond that. So any questions there?
So are they now able, in the second group of authors, they avoid shuffle here?
Right. So the second group, Carlson and Blomkov, does not rely on the shuffle theorems. The shuffle theorem is a purely combinatorial statement. It says, okay, forget all about algebra, forget all about geometry. We have nabla En. How do I take nabla En and expand it in terms of, well, sure, functions are too hard, but what about just in terms of the x's, in terms of monomials? So Hagelin, Heyman, Luhr, Rimmel, Ulyanov, they had a conjecture for how this should be done. And the expression looks a whole lot like this, but we just have to multiply by an appropriate Gessel fundamental quasi-symmetric function corresponding to an inverse descent set. So that's a purely combinatorial statement, right? So Carlson and Blomkov do not rely on that in any way. They say, let's just start with this DRN quotient, right? And let's try to ignore Hilbert schemes, throw them out the window temporarily, and let's try to study this object algebraically. And amazingly, using this theory of affine-Springer fibers, they can show that this quotient has the appropriate vector space dimension, and also that it has the appropriate bigraded Hilbert series, and even that it has a basis, right? So there's, they construct the first actual monomial basis of this quotient that had been conjectured by Hagelin and Luhr. And this is entirely independent of the work of Heyman. It's independent of the shuffle theorem. Is that making sense, Teddy?
Yeah, it's making sense. Just a follow-up on this one. How easier is the proof if you specialize only to Q and avoid T?
Let's see. So the proof that you have, so the proof of any algebraic fact is always hard. Like even showing that this has the correct vector space dimension is difficult. And if I recall the history correctly, when Mark Heyman proved points 1 and point 2, that they had actually sort of, I think, reduced the problem to, if we can only show it has the right vector space dimension, we're good. So even showing that this thing has the right vector space dimension is just extremely hard. And that's what Carlson and Blomkov were able to do in particular. Now, instead, if you're talking about shuffle theorem related questions, which remember is in the combinatorial world, these things really do become easier, right? If I were to say, let Q equal 1 or let Q and T both equal 1, proving an equality of expressions like this, or really I should say this, upon taking the Hall inner product with P1 to the N, that becomes substantially easier.
All right.
Okay. Anything else? All right, so this material was sort of history, and now we're going to accelerate history to the beginning of 2019 and a conference in Banff. So we're going to think about an object called the superspace ring. And what is this thing? Well, formally, it's going to be a polynomial ring and in variables, tensor over the complex numbers, and exterior algebra with n generators. And I'm going to call these generators theta 1 up through theta n. And I'm going to hideously abuse notation when referring to this ring. And write it as so, right? So if you want to operate within this ring, the rule is that the x variables commute. Any x variable commutes with any theta variable. And the theta variables anti-commute. And in particular, because our ground field is characteristic 0, this means that any theta would square to 1. So another way I'm going to write this ring is omega n. And this should recall the idea of differential forms. So I have affine in space, and what I'm looking at are these objects that we all saw when we took multivariable calculus, these differential forms, and these differential forms, well, I guess really strictly speaking, should be polynomial valued and holomorphic, but that's kind of the basic idea. And in that context, we'd usually write these theta variables as dx's. So the theta notation comes from physics, in fact. So I understand that in physics, the word super comes from super symmetry. So I guess in supersymmetry, it's some theory of elementary particles in some sense, where you have two kinds of particles. You have bosons represented by the x variables and fermions represented by the theta variables. And supersymmetry is telling you some kind of a relationship between the bosons and the fermions. And well, I have a colleague who looks at supersymmetry, and I'll try to talk with him so I can say more intelligent things about that. But that's about as far into physics as I'm going to go. So we have this superspace ring that had been studied in physics rather extensively, but until recently, I would say, was not really studied as much within our community. Okay, so again, we have a diagonal action of Sn on omega n, right? And just to be absolutely clear, this is sending a variable xi under the action of a permutation w to xwi, and a variable theta I to theta w of I, like so. And well, with the previous examples as motivation, we can define a module by taking omega n and modding out by the space of Sn invariance with a vanishing constant term. Okay? So I'm going to call this quotient Srn, and it is the superspace co-invariant ring. And well, as before, it's going to be a bi-graded Sn module, with one grading now coming from the x's and one grading coming from the thetas. And unlike in the case of the diagonal co-invariance that we saw before, where the role of the x and y variables was completely symmetric, the roles of the x's and the thetas really are very different now. The x's commute and the thetas anti-commute. So in a sense, when we go to this supersymmetric world where we're breaking a certain kind of symmetry, but we're going to kind of look at what happens when you do this. So questions at this point?
Yeah, just curiosity here. I know you have this fermionic behavior with a minus sign, an important minus sign. Now, to make it quantized, what if you replace -1 with q?
So what if I replace
the negative
-1 with q? If I say theta I, theta j equals negative theta, or sorry, q
yeah.
times theta j, theta I, right? So I know this is something that I've looked at before.
I see.
And I think the point would be right? That if Q is anything other than 1, and if we think of Q as like a complex number or something, that's still going to imply that theta I squared is 0, right? Because that would tell you that theta I squared is like, 1 minus Q times theta I squared or something like that. So I think that you get behavior similar to the case of superspace, but I'd have to double check. There might be other issues.
Yeah, the presence of the Q is to make it non-commutative. That's my idea.
That's right. So it's non-commutative, but it's interpolating in some sense between the superspace setting and the polynomial ring setting.
Okay.
So yeah.
That's okay.
All right. Anything else? Okay, great. So this is the superspace co-invariant ring, and I just kind of want to, before we kind of plow ahead, highlight some classical work of Solomon. So superspace has actually been considered in the context of invariant theory, and in fact, the invariant theory of complex reflection groups. So I'm really happy that Emmanuel asked that question about more general reflection groups. So let me talk a little bit about some work of Solomon. And maybe one way to motivate this work is to say, well, in the case of commuting variables, right, we like to talk with our computers about these quotient rings, and to do that, well, we need some kind of a presentation for this ideal. It won't really do to say we have this vector space generating an ideal. We actually want, of infinite dimension generating an ideal, we actually want a nice generating set. So you might ask, what does this invariant ring look like? And actually, in this setting, I don't just have to look at the symmetric group. I can look at an arbitrary complex reflection group C, G. So you can think about this as being really analogous to the question of Chevalley, right? So if I have an action of a complex reflection group on a polynomial ring in invariables, Chevalley says that the corresponding invariant ring is in fact a polynomial ring. So now I have these invariables, but also differential forms, right? So I have these theta variables appearing too. So what is the corresponding space of invariants? And Solomon has a beautiful answer here. So theorem due to Solomon. So I'm going to let F1, F2 up through Fn and C brackets Xn super G be a system of invariants. And I remind you that this means that my invariant ring is in fact a polynomial ring over F1, F2 up through Fn. Then this object, so if I look at this subspace of invariant differential forms, well, one thing to observe is if I take an invariant differential form involving thetas, and if I were to multiply it by an invariant polynomial, what I would get is still invariant. So it's a module over this ring, but importantly, it's a free module. So that's kind of the first surprise. And not only is it a free module, but there's a very nice generating set. So with generating set, or with basis, I should say, given by expressions of the form dfi1 times dfi2 up through dfik, where I1 up through ik is an arbitrary set of indices, which we should assume are increasing, running between 1 and n. And what's d? Well, d is an operator on polynomials, or even more general differential forms. This is the thing that appears in de Rham cohomology. It's the total derivative operator. Usually you would write it with a dxi, but we're using thetas and not dx's. And we might call this thing the Euler derivation. Okay, so we have an absolutely beautiful structure of this invariant space. Let me just say, why is this relevant in our world of computation? Well, if I wanted to think about SRN, I can write, say, any system of invariants for these symmetric groups, say the E's. And now I just throw in essentially the derivatives of the system of invariants. And I have a quotient I can put into the computer. So many questions at this point. And before I get into the superspace covariant conjectures, I'd like to talk a little bit about, why was Solomon proving this theorem? So, this is it's a really short paper in the Nagoya Journal of Mathematics. And it's really remarkable, right? Because he proves this theorem, which is already an amazing structural result. But he was actually interested in something else. So this was a result which was originally proven by Shepard Todd, or actually, haven't taught for a while, I should probably lasso this. Copy. Paste.
Well, Brendan, I have a question.
Yes, thank you.
Yeah, so this df, the Euler derivation, is that a definition?
Oh, yes, sorry.
Okay.
Thanks.
And then above that, there's these dfi sub j's.
Yeah.
What are those defined? What are those defined?
Oh, sorry about that. Right, so you take these f's, and these are ultimately polynomials, so they're like the e's or the p's. You apply this Euler derivation to each of them individually, and now you get elements of the superspace ring, so they involve thetas, and superspace is a ring, so I can multiply them together. So sometimes you would see like little wedges appearing between these things with some authors, but I'm kind of omitting that. Does that make sense?
Yeah.
Cool. Anything else?
Yes, Brandon, and
Okay.
while you're at it, and this basis, it's a K form, and what's K? Can it be 1, 2?
It can be any number between 0 and n.
Okay.
Sorry, I have a remark. Yeah.
Yes.
Yeah, I think in your definition of Euler derivation, you don't want the f sub I, you just want the
Oh
f.
yeah. Oh gosh. Yeah. Sorry about that. Thank you. It's getting a little too many eyes. Anything else? All right. Great. So again, like why was Solomon actually doing this? Well, there's a corollary of this result, and this corollary was originally proved in a case-by-case fashion by Shepard and Todd. So this is case by case. But Solomon used the structural result to give a uniform proof. So in reflection group land, uniform proofs are the things that we aim for. And what does this result say? It says that if I look at the sum over all elements G in my reflection group, and I'm going to introduce a variable T. So how am I going to weight G? Well, I can look at the fixed space of G. So this is just the set of vectors V in Cn, where if I take the matrix G and multiply by the vector V, I get V back. So this is a subspace of Cn, and I can certainly take its dimension. Well, what I get factors very nicely. It factors as T plus D1 minus 1 times T plus D2 minus 1 up through T plus Dn minus 1. Where what's Di? It's the degree of Fi, and these things are the fundamental degrees. So in Chatelet's theorem, the invariants F1 up through Fn themselves are not unique, but their degrees in fact are, and this is kind of reflected in the symmetric group. You know, we have systems of invariants like the E's, the H's, and the P's, which are certainly all different polynomials. But if you look at their degrees, you always see 1, 2, 3, 4 up through n, right? And if we specialize to the case of the symmetric group, what we're going to get is as follows. So I'm going to have a sum as k goes from 1 to n, and dimension of fixed space, if I'm thinking about the action of a permutation matrix on C to the n, that's essentially telling me number of cycles, right? So I'm going to have Cnk times T to the k, where what's Cnk? This is going to be the number of permutations W and Sn with k cycles, right? Otherwise known as the Stirling number of the first kind. So this is a polynomial in T, which is going to factor as T times T plus 1 times T plus 2, all the way up through T plus n minus 1. And this is a result we often prove in our undergraduate combinatorics classes. So this is really telling you something about the symmetric group. It generalizes in a very nice way to any complex reflection group. The proof that was originally discovered by Shepard and Todd was case by case. And then Solomon used Superspace to give a uniform proof, and a uniform proof of this thing involving Stirling numbers of the first kind. So again, I'll kind of pause. So what I think is so cool about Superspace coinvariant theory is that we're basically going to try to trade the Stirling numbers of the first kind for the Stirling numbers of the second kind. So these are, in many contexts, combinatorially dual objects. And in this context, this duality, at least conjecturally, comes from taking a quotient ring. And this is, you know, in some sense, something I find very, very interesting about this family of conjectures.
Brandon?
Yes. Yes.
And now I'm a little puzzled. In the bottom one, if you replace t equal to 1, then you get the factorial, which is to be expected. Stirling equals factorial summation. And in the Shepard-Solomon theorem, if you replace t equal to 1, then it tells you the size of the group is d1 time up to dn product, right?
That's right.
So that means the degrees are related to the size of the group.
Absolutely. So, so the degrees are magical. The degrees control just way too much information than they had any right to. And one classical result about the degrees, and this really kind of comes from the Chevalley structure theorem, is that the product of the degrees is exactly the same thing as the size of the group, right? So if you believe the Chevalley structure theorem, you can derive that result using some generating function magic. And by using kind of analogous generating function magic, if you believe this structural result of Solomon, you can derive this thing, or Solomon derived this thing, in fact. Does that make sense?
Yeah, good.
Cool. All right. So finally, in the last 10 minutes, getting to what happened 3.5 years ago. So we've got SRN, which is, again, this bi-graded SN module. And you can ask, well, what's the vector space dimension? What's the ungraded SN structure? What's the bi-graded SN structure? What's the Hilbert series? And each and every one of the answers to these questions remains a conjecture. So this is a family of conjectures. And as I understand, maybe the best way of citing these is the Fields Institute combinatorics group. So I asked Mike Zabrocki about this. You've got people like In Bergeron, Mike Zabrocki, John Chachek, and probably others. And this conjecture is supposed to be telling you things about this ring. So conjecture part 1, as an ungraded SN module, SRN is isomorphic to, well, it's not permutations, it's not parking functions, but now it's this thing OPN, which is going to be the family of ordered set partitions, B1, B2 up through BK. So I believe these appeared in John's talks. Of the set of numbers between 1 and n, right? So an ordered list, decomposing that set into non-empty blocks. So this carries a natural permutation action of Sn. And this is almost correct, but to make it actually be correct, we have to, again, do a little sign twist like that. Okay, so that's still open. Conjecture part 2, again, still open. What if I want to look at the bi-graded Hilbert series of this object? Well, now I need 2 variables, but I have to be a little bit more careful in some sense, you know, with respect to the diagonal covariant case, because my x variables and theta variables are playing different roles. So Q is tracking x degree, Z is tracking theta degree. And the conjecture says that this bigraded Hilbert series is the sum as K runs from 1 up through N of your theta degree tracker with N minus K. And now I'll have a Q analog of K factorial. And remember how we saw Stirling numbers of the first kind appearing. Now we're going to see Stirling numbers of the second kind. But it's going to be a certain Q deformation. Like so. So there are several different ways you can Q deform the Stirling numbers of the second kind. This is a Q deformation that was studied by Michelle Wachs and worked with Dennis White. So what you do is you take the Stirling recursion that looks like this. And we're supposed to somehow Qify this thing. So we'll put some Q's there. And there are a few kind of different choices for how you might insert a Q into this expression. And the way we're going to do it is like that. And of course, we need some initial conditions. And oops. They're going to look as follows. So SQ of 0K is going to be 1 if K is 0 and 0 otherwise. Okay.
Brendan?
Yes.
A couple of things. First of all, these Q Stirling numbers go back to work of Carlitz in 33.
Okay.
So way before Wax and White.
Sure, yeah.
They did great stuff, but and the other thing is that if you want to start at n equal to 0, you want your summation to start with K equal to 0.
I want to start at n equals 0. I want to start, oh, yeah, SR 0, I think, would be the ground field.
Yeah, exactly. So,
yeah, well,
anyway,
yeah, we can.
Small point.
Okay, we can turn a 1. I can turn a 1 into a 0 relatively easily. All right.
As you just proved.
Yes. Maybe I can't prove this conjecture, but I can turn a 1 into a 0. All right, and finally, part 3, what about the graded Frobenius image in Q and Z? Well, conjecturally, and I guess we'll start at 0 just to be safe to those who like to study the objects with 0 variables. I've got a Z to the n minus K here. And now I have these delta operators, which appeared in Anna's talk. I'll use their prime diversion. We'll have an E sub K minus 1 acting on EK in the specialization where T is sent to 0. Okay. And there's also an expression due to, well, essentially Andy Wilson for a Schur expansion of this object. So there's a Tableau formula for this thing, which is very much in the spirit of what was discovered by Lustig and Stanley. Okay, so these things are all conjectures, and in the 1 minute I have left, I would like to tell you the progress that has been made, which is not so much. So 1 bit of progress on 2. We can show that, use my lasso skills. This polynomial expression, shrink. We can't actually show that equality but we can show this thing. So when I write an inequality of two polynomials, what I mean is that their difference is a polynomial with non-negative coefficients. And this, I'll say, is due to the Fields group. Also, if I were to look at the Hilbert series, of the alternating part. So if I look at SRN, and if I look at the sign isotypic component, so this is a bigraded vector space, I'll just say it's correct. You can actually write down a combinatorial expression for this thing involving partitions fitting inside a box. I won't do this. This is a result of Swanson and Wallach. There's a very interesting recent paper of Bruce and Josh Swanson looking at a version of this quotient ring in type B. But stuff remains frustratingly out of reach, right? We can't even show that this quotient ring has an appropriate vector space dimension, right? And what I'll talk about next time is work I did with Andy Wilson that, and again, in a sense, sort of says that this is a very frustrating situation. We're going to throw this out the window. We'll try to look at another superspace model involving now these superspace Vandermonds, where we actually can prove the analog of this conjecture. And we're going to present a bridge conjecture, kind of in the spirit of what John and Michelle did in their work on Hessenberg varieties. This bridge conjecture is still a conjecture, which, if you could prove it, would imply this Fields conjecture. So that's, I guess, what we'll do next week. So thank you very much. Sorry to have gone over.
Great. Any questions for?
Yeah, so I just had a great talk, Brendan. Very nicely done. I just wanted to comment on this paper that Josh and I did recently. We don't just consider type B, we do have a actual basis, combinatorially defined basis for SRN in both types A and B, which would trivialize, if you can show that the basis is actually a basis, then you get the Hilbert series for free. So, but it's very frustrating that we have this really nice description of a really nice basis, and we just can't prove that it is a basis. So if anybody is interested in working on that, I would love it, and I'm happy to talk with anybody, send them copies of the paper, whatever, because it's been gnawing at us for a while now, and there's some key observation that needs to be made if these things are actually bases. But as I said, if they are bases, we're done with two.
Absolutely. This is a frustrating area in some sense. And what makes this even more frustrating is we know lower bounds for the dimensions of these quotient rings. So in principle, all you have to do is take any monomial, take your relations in your ideal, and combinatorially use these relations to express your monomial in terms of the purported basis. And you will have proven, well, not the SN structure, but certainly the Hilbert series part of this conjecture. But we don't know how to do that. So this is something that really is going to involve some bit of combinatorial cleverness, some bit of a straightening algorithm that you, me, and a lot of people are just missing.
Brandon?
Yeah.
In number 2, the Hilbert series, now actually it seems like you can, now if the expansion is correct, then you have unimodality in the parameters.
Well, so what do you mean by unimodality, right? Because I have two variables.
Right, so in each variable.
So if I fix a power of yeah, so certainly if you fix a power of Z, you do have unimodality here. That's correct. Now, if I fix a power of Q, I would have to think about that a little bit, but that may be correct, and yeah, I just can't really quite do this on the spot.
Thank you. Nice talk.
You're welcome.
Any other questions? It's not. Okay, so we'll see you on Tuesday.
Thank you so much. Really
Great.
nice talk.
You're welcome. See ya.
All right. Have a nice weekend, everyone.
Bye.
Bye. Thank you.
You're welcome. See ya.